Talking about binomial probabilities and how something is considered binomial. So we go through those 4 fun conditions, okay? And then what we saw was the hand way or the formula way to calculate any binomial probability. Then at the end we were doing binomial calculations using our calculator. And we found that using our calculator makes it really nice, especially when we have to find the probability of multiple probabilities, like the sum from like greater than a number or less than a number. So what I want to do to start us off here is if you flip to your next page of notes, which most of you are here on the examples, is to run through the first example with you, okay? And you'll want to have your calculators out because we'll definitely be using them to do the binomials, PDF and CDFs, and identify which one you use when. So, in number 1, and really with all these binomial problems, one of the things that I do is just kind of in my mind run through the 4 steps just to make sure it is binomial. So in number 1 it says, suppose in a certain large city 80% of households have a DVD Blu-ray player. Let X equal the number among 10 randomly selected households that have a DVD Blu-ray player. So if I think about this, is it a binary, meaning is it a success or failure? Well, yes, either they have a DVD player or DVD Blu-ray player, or they don't. Okay. So independent, does one person owning a Blu-ray DVD player impact another person? More than likely not. Okay. The number of fixed trials. Well, they tell you right here that that number is 10. So I go ahead and identify it as which variable it is. It's our n. It's the total number of fixed trials. Then I want to identify my p-value. What's my probability of success? Well, it's 80% for each and every person that's selected. So I know it does satisfy this binomial setting. So I can go ahead and use binomial PDF and binomial CDF. So on the first one here it says find p of x equals 7. So in order to find that, first thing I look at is it an equal? Is it a less than? Because if we remember, equal means I use the PDF, less than or equal, I use the CDF version. So since this is an equals, that tells me I'm going to use binomial PDF. So now the numbers that we enter in our calculator always go in the order N, P, and K. K is the number you want, the number of successes. So we want to find or get exactly 7. So we're going to go 10, comma, 0.8, comma 7. So now, on our calculator, we can just simply enter it in, second bars, just like we were doing normal PDF and CDF, but we got to scroll to the next screen and go to binomial PDF. Just type them in, 10, comma, 0.8, comma 7, hit enter, and we have our probability here, 0.2013. Great, we got our answer. But what does that value mean in the context of the problem? So we want to say what that actually represents. So the probability that we get exactly 7 out of 10 households with a DVD / Blu-ray player is 0.2013. Why do they call it what?
Blu-ray.
Good question. Don't they, like when it hits the light, doesn't it like reflect something that's blue?
No, the light that they use is blue because it's something about the frequency.
Alright.
Just a higher quality. Yeah.
Yeah, higher quality image, so like the laser that reads it is blue, or?
Yes, the laser that reads it.
Okay.
And they just have it on the bottom of this as sort of protection.
Okay. Because I know like when you grab a Blu-ray, like when it hits the light at certain angles, it's blue.
I don't even know what you're saying.
So, I think that's kind of cool. Alright, so, let's take a look at the second one. Switch colors. So in B, it says find P of X is less than or equal to 4. So in this case, it actually has the less than. So I am doing CDF. So binomial CDF, again it's this NPK, and I get 10, comma, 0.8, comma, 4. So, let's go ahead and plug this in. Now that it's a cumulative, we're adding basically 4 or less, 3 or less, 2, 1, and 0. So we're adding all of those calculations up. So we let the calculator do all that adding up for us. So binomial CDF, 10, comma, 0.8, comma, 4, 0.0064. Yeah, I think it's so, how do we interpret this? Well, the probability that we get 4 or less households out of 10 that own a DVD / Blu-ray player is 0.0064. All right, C. Says find the probability that X is between 2 and 8, including 2 and 8. Okay, and what does this value mean in the context of the problem? So what I like to do when doing these problems at first, when doing them and explaining them, is I like to look at all of the outcomes and visually see what does it mean to be, between 2 and 8. And how can we use these functions to help us set it up? So, the actual number of outcomes that are possible in this binomial situation is we could get anywhere from 0, people saying they out of 10, let's say they have a DVD, Blu-ray player, all the way up to 10. So those are all of the possibilities. So when looking at all of these possibilities, ideally, I want between 2 and 8. Now, there isn't a simple binomial function on our calculator that does the in-betweeners. Okay, bummer. However, we can use the functions that we have to get this. It will just take a couple calculations. First of all, if I think about this, I could start off by saying, all right, how do I get all of the outcomes that are 8 or less? What would I use? Okay, I could use binomial CDF and start it by saying 10, comma, 0.8, comma, 8. That's going to give me all of these probabilities from 8 to 0. Evelyn, please keep your phone away. Thank you. Now, I do not want 1 and 0 to be included in my solution. So what I can do is say, all right, let's subtract those outcomes away. So how would I use binomial CDF to represent those outcomes I want to remove? What would I start off with?
10.
Yeah? Does P change?
No.
But what should this number here be? Well, it should be 1 and 0. We don't want it to be 2 because we want 2 to still be included in our solution. So you have to watch the inequality signs. Here, I wanted 2 to be included in my solution. That's why this number goes down to 1. If I were to actually remove the equal sign, then this number actually here at the end would actually be at 2. So you got to watch the signs carefully. However, what's really nice is once you have this set up, it will give you your calculation for the in-between. So you can type this all in at the same time. So we can go second bars, binomial CDF, 10, comma, 0.8, comma, 8. And then I want to subtract. Do it again, second bars, binomial CDF, 10, comma, 0.8, comma, 1. I hit enter, 0.6242. For a second. So again, we want to explain what this value means. So the probability that we get between 2 and 8 households out of 10 that own a DVD Blu-ray player is 0.6242. How are we doing so far? Yeah.
Why is it 1 in the second one?
Okay. So the first one's 8 through 0. I want 2 to actually be included in my result. So I have to subtract out just 1 and 0. So I want the sum of 1 and 0 to be subtracted. And that is, we get that by going from 1 or less. If we make this a 2, you're going to be subtracting from 2 or less. And you are leaving out the probability of 2, which you want included in your answer.
So if you wanted 3 to 8, then you would.
Then this would be a 2. Yeah. But here's the trick part of it though. It's because of the equals. If I remove that equals, okay, then this would be a 2. Okay, so watching your inequality signs is going to be important. Making sure, are we talking about less than, does it say less than 4 or less than or equal to 4? Because that determines, do you include 4 in your answer or not in your answer? Okay. All right, let's have you do this. Let's have you for about the next 5 minutes here. Look at number 2. Okay, in your groups, work together. Okay, and let's look at number 2, A, B, and C. Use the ones above to help guide you. I'm going to pause the video so those of you who are actually watching it, try number 2 and then start the video and we'll show you your answers. Alright, so what I want to do is make sure I give you a chance to see how you guys did with your answers. So, for number 2, we're talking about Sarah and her capability of answering any type of trivia question. So, take a look at your answers up here and check. So on the first one, you're looking at exactly 3. That's why we're doing PDF. Okay, 8, 0.65, 3 is 0.0808. So we'd say the probability that Sarah will answer exactly 3 out of, or exactly 3 trivia questions. I probably should have maybe even said out of 8 questions correctly is 0.80 or 0.0808. On B, it's a less than or equal to 6. So that tells us we're using CDF. So 8, 0.65, 6, 0.8309. So the probability that she answers 6 or less questions is 0.80 or 0.8309. And then of course our last one there, this is the one where you have to put the 2 together. Okay. So on this particular one we're doing 7 or less and then subtracting 2 or less. So binomial CDF from 7 minus binomial CDF from 2 or less, we get 0.9428. All right, questions? Beautiful. Let's continue on then with our notes and continue our work with binomial distributions. So right now, 3 of you have your phones out. Again, phones physically away. I don't want to send you out of here because that will be my next step. Thank you. And yes, that is on tape. So, binomial distributions. One of the neat things that we can do with binomial distributions, just like the distributions for a discrete random variable or a continuous random variable, we can calculate out its mean and standard deviation. Okay? We can do those by using these 2 formulas. The mean of any random variable is simply calculated by taking the number of trials times its probability. So like in Sarah's trivia question problem, her mean would be, well, she was answering 8 questions. The probability of success was 0.65. So on average, she will answer 5.2 questions correctly. The standard deviation is actually a much easier calculation than some standard deviations, but it's the probability, or you can look at it as the number of trials times the probability of success. If you want to think of, and you'll start seeing me refer to 1 minus p as the probability of failure. I can't even say it right now. Because if the probability of success is p, 1 minus that will be the probability of failure. So in our case here, we wanted to calculate out the standard deviation for Sarah and her trivia questions. we'd have the square root of 8 times 0.65 times 0.35. And this would tell us, basically on average, okay, how many questions right would it deviate on average from the mean. So, I could take, whoops, wrong. So I can go square root 8 times 0.65 times 0.35 equals about 1.35. So on average, the number of questions she's getting correctly will vary from the mean by 1.35 questions. Kind of nice to know. Now, two concepts that can come up with binomial distributions that we want to talk about here today can be very helpful to start to estimate probabilities when instead of having, 10 questions or 15 questions, what if we were doing, 1,000 questions or 500 questions? The nice thing is your calculators can still do all that fun calculations out. But we still can find ways to estimate the probabilities. And these formulas are still used widely in statistics, and at the same time, our calculators still can do these binomial CDFs pretty quickly. But the first thing I just want to talk about here is this concept of sampling without replacement in binomial distributions. One of the issues sometimes that happens when we talk about binomial distributions is checking for independence. Right? Once in a while, the probability of one outcome could influence the other outcome. Like for instance, when I'm talking about a deck of cards, I'm taking a look at what's the probability that you draw a heart. Well, if it's on just the first card, there's 26 red cards out of 52, 1/2. But if the first card is a red card and I don't put it back in, it influences the probability of the next draw. Okay? In many situations, that can impact and not allow you to do a binomial distribution. However, what we have seen and statisticians have explored is that, well, if you start to take a look at large samples, and those samples come from very large populations, the probabilities really don't change very much. Okay? They change very little. Because of that, it really has very little to no impact on your final answer. So one way we can check for that, for independence, is, especially when we're sampling without replacement, is to check, is the population that we're sampling from greater than or equal to 10 times our sample? If that is the case, then this whole idea of sampling without replacement doesn't impact the independence piece. The probabilities, yes, they are different, but the size of the differences in the probabilities is so small that it barely changes the probabilities or your outcomes. Now the second thing is, and this is what we would use, or I should say I would use quite a bit to estimate binomial situations when we had a much larger number of trials. Okay? And we would use what's called a normal approximation for binomial distributions. You can actually estimate, okay, a binomial probability using the normal curve. But the approximation is only reliable if two conditions are met. Okay? You should only use the normal approximation if the number of successes that you're looking for, n times p, is greater than or equal to 10, and the number of failures is greater than or equal to 10. If that's the case, then you can actually use the normal curve to estimate a binomial probability. And what's nice about that is then you can use the mean and standard deviation of a binomial distribution for your normal curve. So it all comes back to chapter 2 yet again. Okay? So all that stuff on binomial distributions we're going to be doing here today. So now, if we go to the next page of notes and take a look at our example here, we'll put it into play. I apologize for all the typos on this page. Okay? For some reason, I type in the word debt instead of debit about 5 times, but I do have debit in here one time, and you'll see it come up quite a bit. So it says, in a survey of 506 teenagers, age 14 to 18, subjects were asked a variety of questions about personal finance. One question asked teens if they had a debit card. So there's the first time it comes up.
My card has so much debt.
Suppose that exactly 10% of teens age 14 to 18 have debit cards. See, it's spelled right there. Shoot, got it right one time. So, it says let X equal the number of teens in a random sample size of 506 who have, well, there's debit cards.
Probability of Bart's getting it.
Probability that Mr. Burns spells something right.
1.
Well, pretty darn good. I only misspelled, what, 2 words up there?
Yep.
Still pretty high. Okay. So, A says, show that the distribution of X is, and I apologize that says approximately binomial. Just show that it's a binomial situation.
It's kind of like
Either it's binomial or it's not. It's not approximately binomial. Can be approximately normal though.
appropriate.
Yeah. So, what's the first thing I check for it to be binomial?
Two
Huh?
things.
2 things.
Yep, so we talk about bins. So is it binary? Do you have 2 things?
Yes.
So either you have a debit card
Or a debt card.
or you do not. So this is definitely a yes. It's binary. You have a debit card or you don't. Those are only 2 choices. You don't kind of have a debit card.
Your parents old.
All right, B, independent. Now this is where what we were talking about on the previous page comes into play. Are we sampling here without replacement? Meaning, are we selecting a person and not putting them back in to be selected again? When you're selected, can you participate in the survey twice? No. So we're actually sampling without replacement. So when we are sampling without replacement, we need, whoops, I just wrote Ned. We need to check to see if our population is greater than 10 times our sample. So in our case, is our population greater than or equal to 10 times 506? Is our population greater than 5,060? Yes. So this is a yes. There are more than 5,060 teens. Did they say in the United States here? I don't think they did they? But I think we're, yeah, in the population. They don't specify specifically, so I'm going to kind of assume You could even say a large city and you'd be fine. So the only time I would worry about it is if they actually said the population of a town was 2,000 people, and then they surveyed 516 or something to the extent of that. Then I'd be a little more concerned about it. But most of the time, that population piece will be met. All right, what's 3? What's N? Number. So what's the number of trials? Is it fixed? N equals 506. I'm gonna start having a coughing attack. Woohoo! I'm loving this bronchitis. All right, what is S? Excellent. So what's the probability of success?
10%. Oh.
Okay, I apologize, but check. And the previous one was a check too, so they all check out. So we're good to go. Binomial. B. Switch colors here. Check the conditions for using a normal approximation in this setting. Okay? So, this is where the number of successes and the number of failures have to both exceed 10. So, N times P, well, 506 times 10%, that's 50.6. That's greater than or equal to 10. Excuse me. And, bless you, 506 times 90%, 455.4 is greater than or equal to 10. Check. I know.
Maybe Thanksgiving will do you good.
Yeah, my wife is wanting me to take a day off of school.
Yeah.
But I keep telling her I care so much about the kids.
Well, thanks very much.
I can't be gone from my kids. They miss me too much.
True. Just have to listen to you.
Alright, C. What are the mean and standard deviation for this setting? So that's where the formulas come into play. The mean of X is N times P. We actually did that already. Can we do that right up here? That's what I like about these formulas is you actually, the mean and the number of successes are the same thing. Standard deviation, now we're doing the square root of N times P times 1 minus P. So the square root of 506 times 0.1 times 0.9. So square root 506 times 0.1 times 0.9. So 6.75.
That was recorded.
It's fine by me.
That will encourage the person.
I'll stand by my words. I always will. Alright, so now I have my mean and standard deviation. It says here, use the normal distribution to estimate the probability that 40 or fewer teens in the sample have debit cards. Well, most. If this was like 19-year-olds, most would have probably dead. I know this is being recorded, but I jokingly will say I am worth more dead than alive. But it's true. Yes. I have life insurance policies on me. So if I were to die, my wife would receive a large sum of money. Correct. Would I need any money?
No, I'm not saying that
Yeah.
you would, but if you don't have any possessions, then you are worth zero.
Right.
Yeah, you need all your.
But what I'm saying is, I'm worth more dead than alive because there's more money. My life insurance policy has more money that would get paid out to my wife than we currently have.
That means your wife is worth more when you're dead than alive.
Correct. That's why I'm saying I'm worth more dead than alive. Yeah. Alright, so, yes, we got that all on tape. Sorry for those of you who had to listen through that. So. So we want to know what's the probability that x is less than or equal to 40?
0.289.
0.289? Did you just make that up or did you actually calculate it?
Made that up.
Okay. Well, let's see how well you made it up. I think you are off by about 0.15.
Wait, what did you say?
That's not that bad. I'll take that.
So, it's normally distributed. So, according to up top, my mean was 50.6.
I can never make this damn. I can never make these little.
If it's really hard, just make a mound. Okay. It takes years of practice for some.
Yeah.
Seriously.
Alright, 6.75 standard deviations. Well, 40 is about 10 units away. So I know it's somewhere between 1 and 2. So I'm going to put 40 here. I'm looking for this area right there. Ooh, normal curve, looking for an area. I want a excellent z-score. Your score minus the mean divided by the standard deviation. So, my score, 40. The mean was 50.6. The standard deviation, 6.75. Calculator time. So, 40 minus 50.6. Negative 10.6 divided by 6.75. Negative 1.57 standard deviations. So I'm really looking at what's the probability that z is less than or equal to negative 1.57. So, we go normal CDF. You got it, negative infinity to negative 1.57.
See how close Carter was.
I am saying he was about 15% off.
That's pretty good.
So second part,
Pretty good for a guess.
normal CDF,
It's like a D.
negative 999 to negative
Twist ending parts is 50% off.
1.57, 0.0582. Oh, we were like 23% off.
Carter, go home.
You were 23% off and I was 8% off of what you said. So,
Carter's gonna save a lot of money in his car.
so,
Switching to Geiger.
exactly. The probability that 40 or fewer teens have a debit card is 0.0582. The one thing about this particular problem that I do find interesting